Hello, I'm Amir Mohammad Karimi Mamaghan, and I'm going to present the paper Analysis of Address Lifespans in Bitcoin and Ethereum. Here is an overview of this presentation. First, I start with an introduction to Bitcoin and Ethereum. Then, I briefly go through related works and discuss their results. After that, I explain the methodology and contributions of this work, and finally, in the end, I will mention the results and possible future works. A cryptocurrency is a digital currency which is an alternative form of currency created using encryption algorithms. They are mostly decentralized. Decentralization generally alludes to the transfer of supervision and decision-making from a centralized association, for example, an individual, a corporation, or a group of people, to a dispersed network. And most of them have the anonymity property, which means that there's no real identity involved in a transaction, and transactions occur between addresses. But it's better to say that they have the pseudonymity property because there are ways to link addresses to users. Bitcoin is the first cryptocurrency created. It was introduced in 2008 by an anonymous developer or group of developers using the name Satoshi Nakamoto, and right now it's the most popular cryptocurrency in the world. It consists of a linked list of blocks called blockchain. Each block in the blockchain has many transactions, and each transaction is similar to a regular bank transaction, sending money from one or several addresses to others. And one of the important features of Bitcoin and most cryptocurrencies is that its blockchain and transaction data are publicly available. As we mentioned earlier, there is no central authority present to validate and verify the transactions, yet every transaction in the blockchain is considered to be completely secured and verified. This is possible only because of the presence of the consensus protocol, which is a core part of any blockchain network. A consensus algorithm is a procedure through which all the peers of the blockchain network reach a common agreement about the present state of the distributed ledger. The consensus algorithm of Bitcoin works as follows. First, nodes broadcast new transactions in the network. Then they collect new transactions into a block and build a block. After that, a random node broadcasts its block into the network. Others will check the validity of the block and its transactions, and if they approve that, they include the block's hash in the next block. Another popular cryptocurrency is Ethereum, which was introduced by Vitalik Buterin in 2013. It has a complete Turing machine called Ethereum Virtual Machine that can run different programs, which are called smart contracts. The structure of blocks and transactions in Ethereum is somewhat similar to Bitcoin. And just like Bitcoin, Ethereum's transaction data is publicly available. And as we mentioned earlier, a transaction occurs between one or several addresses. Addresses are similar to bank accounts, but there's no limitation on the number of addresses owned by a user, so a user can create and have several different addresses. Now let's take a look at some of the previous works on Bitcoin and Ethereum's data. Various analyses were done on cryptocurrencies from different perspectives, and research on cryptocurrencies can be classified into two main categories, monetary and non-monetary. The monetary analysis focuses on the price of these cryptocurrencies and their changes over time. In non-monetary studies, cryptocurrencies are examined from various perspectives, such as anonymity, graph analysis, or statistical analysis. Our work here is more related to previous non-monetary work, so we focus on them and their results here. As you may know, there are a lot of works regarding the analysis of cryptocurrencies data. I summarized the most important ones here. In anonymity, there are a lot of works trying to find out users and cluster addresses so that each cluster corresponds to a user. They use several heuristics to cluster addresses, and some of those heuristics are still valid and usable. In the analysis of cryptocurrencies transaction data, previous works have shown that the degree distribution and also transaction value distribution of both Bitcoin and Ethereum follow a power law distribution. Also, they found out the transaction graph of Bitcoin has a small world property. As its name suggests, in a graph with a small world property, on average, each node can be reached from every other node by a small number of steps. To be more precise, a graph that has a small average shortest path between the nodes and also a high clustering coefficient will have the small world property. Also, from another perspective, there are some works on checking the relation between the number of transactions and the value of the cryptocurrency, and it turns out that actually there exists a high correlation between them. Moreover, there are some other works that calculated a large number of statistical features of Bitcoin and also some other cryptocurrencies and tried to analyze them. They achieved interesting results. They showed that most mined Bitcoins remain dormant and not sent to any other addresses. Furthermore, they realized that there are a huge number of tiny transactions and a small number of large transactions. Another work explored several cryptocurrencies and analyzed their statistical features on a monthly basis. This study also examined the statistical features of the complete datasets and showed the significant correlation between these features and cryptocurrencies' market values. Okay, now we go deeper into this work and its contributions. The main goal of this work is to analyze the lifespan of each address, which we will define later. Also, we want to find the distribution of some features of each address and analyze the relationship between these features. I will introduce the features in the next slide. And for analyzing the lifespan, we are trying to fit a known distribution to it, and for that we use several different distributions such as normal, log-normal, power law, and double Pareto log-normal distribution, or in short DPLN. DPLN exhibits Paretian power law distribution in both tails, and its PDF comes from the state of Brownian motion. It's proven to be helpful in modeling size distributions, such as incomes and settlement sizes. We will show that the DPLN distribution is the best fit for lifespan distribution in both Bitcoin and also Ethereum. As I mentioned before, the complete transaction data of Bitcoin and Ethereum are publicly available. So for Bitcoin, we used Bitcoin client, which uses remote procedure call protocol to collect blocks from the Bitcoin network. We collected transaction data of Bitcoin from January 9, 2009 to March 7, 2021, and it constitutes around 800 million unique addresses. And also for Ethereum, we used Ethereum ETL tool and collected Ethereum's transaction data from August 7, 2015 to August 24, 2021, and it had around 126 million unique addresses. And the features we are going to analyze for each address are start time and end time, which are the first and the last appearance of an address in transactions, lifespan, which is simply the difference between the end time and the start time for an address, turnover, which is the total amount of currency exchanged by an address, and also turnover in US dollars, which is the total amount in US dollars, transaction count, which is the number of transactions an address was participated in, and also the average time between transactions of an address, which is simply the lifespan divided by the transaction count for each address. Okay, now with everything said, let's take a look at the results of our work. In this slide, we can see the plot of the distribution of turnover in US dollars, transaction count, and average time between transactions for Bitcoin in both linear scale at the left and logarithmic scale at the right. As we can see, due to the linearity of the plots in a logarithmic scale, we suggest that the distribution of both turnovers and also transaction count follow a power law distribution. There are a lot of addresses with few transactions and turnovers, and a few addresses participated in a lot of transactions and exchanged huge amounts of currency. And also in the average time between transaction feature distribution, we can see a break in the line, and it consists of approximately 2 lines in the logarithmic scale. And we posit that it follows a DPLN distribution, as DPLN distribution has a similar property in logarithmic scale. And for Ethereum, the result is pretty similar to Bitcoin, so I will not show it. Here we can see the plot of each feature against the lifespan for each address in Bitcoin. Looking at turnover and turnover in US dollars, we observe that the relationship is similar to the power law. There are a lot of addresses with short lifespans and huge exchanges. They might represent the industry addresses that are not frequently used but transfer a great deal of money. And also, there are a few addresses transferring huge amounts of money. They are possibly the addresses created in the earliest stages of Bitcoin but left unused until Bitcoin gained value and popularity. And the final plot consists of a huge uniform part and a part that contains a lot of addresses with a short lifespan and high transaction count. And they probably represent businesses that frequently change their addresses. For example, marketing websites that change their addresses every hour. Similar to Bitcoin, we plotted the features against the lifespan in Ethereum as well. The results are pretty much the same, but there are fewer transactions per address than in Bitcoin, as expected. And finally, we can see the distribution of lifespan of addresses in Bitcoin in both linear scale and logarithmic scale. The plot of lifespan is similar to the plot of average time between transactions, which we discussed earlier. We will fit different distributions to this plot later. And here we can see the distribution of lifespan of addresses in Ethereum. As we can see, both distributions in Bitcoin and Ethereum have characteristics of a power law distribution in both tails, and they almost consist of two lines on a logarithmic scale. And finally, we use different distributions to fit the distribution of lifespan in Bitcoin and Ethereum. We can see the results in the tables. The mean squared error metric is not the best metric for measuring the performance of a regression task, so we use adjusted R squared instead. And for fitting the different distributions, our configurations were as follows. We used normal, log normal, power law, and DPLN distributions for fitting. We used both linear and logarithmic binning to get the lifespan distribution. We used different number of bins ranging from 100 to 2000. And as the outliers are important while investigating distributions, we fitted the distributions when keeping the outliers and also when removing them. And as we can see, the best fit for lifespan distribution in both Bitcoin and Ethereum is DPLN distribution. For Bitcoin, we observed that the adjusted R squared is pretty high on a logarithmic scale, but not on a linear scale. On the other hand, in Ethereum, adjusted R squared is high in both scales, and therefore DPLN fits better to Ethereum than to Bitcoin. And here we see the quantile plot of the best fit of address lifespans for Bitcoin. A quantile plot or QQ plot is a probability plot, a graphical method for comparing two probability distributions by plotting their quantiles against each other. As we can see, the DPLN fit can well represent address lifespans. Finally, we discuss possible future research here. As we could see, our work is fundamental and can be a groundwork for future research. We suggest these possible future works. First, a possible route is to analyze the distribution's changes through time, and not for the whole data together, and find correlations between the changes and events from the real world that affect the cryptocurrency. Another possible idea is to analyze more features together and maybe add some graph features as well. And another path is to build an address graph and compare it to the transaction graph in different aspects, such as connectivity, degree distribution, etc. And our final suggestion is to use lifespan in other applications, such as finding fraudulent users, network attacks, and anonymity. Thank you for your attention.